Ini sudah bisa dimulai? Ini sudah bisa dimulai?
Diponegoro University has been moving ahead to be the best university in Indonesia by providing 13 faculties of undergraduate and postgraduate. Diponegoro University has graduated 300,000 qualified alumnus. Diponegoro University also establishes vocational schools to generate a ready-to-work alumnus. Holding the fighting values of Pangaran Diponegoro, such as honest, brave, fair and attentive, Diponegoro University keeps producing excellent alumnus nationally and internationally, while also contributing in the development of knowledge, technology, art, culture and exercise.
Diponegoro University now is a rising star. We have planned to become one of university in 500 world university rank. We have been continuously improving the supporting aspect such as regulation, facilities, financial that can be beneficially implemented for the society. We are also keen to improve the quantity of national and international academic publication, as well as the number of doctorates and professors in Diponegoro University.
Now, Diponegoro University has been improving in two important aspects of achievement: institutionally and student achievement. Diponegoro University has become a world-class university by being ranked 5th amongst almost 5,000 universities in Indonesia. Meanwhile, the students' achievement in both national and international scales of prestigious events are increasing. The vision to be an eminent research university is supported by the continued increase of research funding. The total research and civil service funding in 2018 is 123.7 billion rupiah. It consists of PNBP, the National Competition Research Funding, and Collaboration Research Funding. The intellectual property right becomes the indicator of significantly improved research. The patent consists of simple patent, patent, international patent, software and invention legal letter. To support the academic process, Diponegoro University has been improving the student facilities. Thus, the students will not only get the knowledge, but also the actualization space. As for the academic service, Diponegoro University has built a central computerized system that includes the service for the online study plan and online registration.
Kompetisi di Undip yang sportif dan konstruktif memacu saya untuk terus berprestasi dalam akademik maupun non-akademik.
Didukung dengan fasilitas umum dan keakademikan yang lengkap.
Sehingga membawa Undip masuk 10 besar universitas terbaik di Indonesia.
Undip berada di daerah beragam budaya yang harmonis.
Yang pastinya Undip lebih baik.
Undip lebih baik. Bagaimanapun, Undip pasti lebih baik.
Silahkan MC untuk mulai. Lukman, Filomena.
Okay, thank you, Bu Nisa, for the class. And Assalamualaikum warahmatullahi wabarakatuh.
Sebentar. Ya, aduh, backup dulu, backup dulu.
Lukman, handle dulu, buka.
Oke, Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Good morning and greetings to Honorable Mrs. Dr. Martini, BSc, MPH, as the head of Epidemiology and Tropical Disease Department from Faculty of Public Health, Diponegoro University, Mrs. Associate Professor Lintang Dian Saraswati, MPH, Epidemiology, as Associate Professor in Epidemiology and Tropical Disease Department from Faculty of Public Health, Diponegoro University, Mr. Dr. Budiono, BSc, PH, MPH, as the Dean of Faculty of Public Health, Diponegoro University, and to our guest speaker, Mr. Associate Professor Ting-Wu Chuang, as Associate Professor from Department of Molecular Parasitology and Tropical Disease, Taipei Medical University, and to all lecturers and participants who have joined this room. We would like to welcome you on Visiting Professor Program 2021, presented by Department of Epidemiology and Tropical Disease, Faculty of Public Health, Diponegoro University. I am Alif Lukman Wijaya and my friend Viremia Larasati as today's Master of Ceremony, and we are glad to have you here in this event. Before we start our event, let us pray together according to our respective religion and faith. Praying starts. Amin. Before we start our event, to all participants, we would like to inform you, please fill in the registration form in the chat room. Operator has shown, please show the link for the presentation. Thank you. And praise the Lord, by His grace, we would be here to enjoy and join this event to gain more knowledge about epidemiology and tropical disease from our great speaker. But first of all, it's time to listen the welcoming speech from Dr. Martini as the head of Epidemiology and Tropical Disease Department from the Faculty of Public Health, Diponegoro University. To Dr. Martini, BSc, MPH, please, this time is yours.
Ya, Bismillahirrahmanirrahim. Respectable the Dean, respectable speaker, Associate Professor Ting-Wu Chuang, respectable Moderator, committee, and also all participants at the scientific Zoom meeting here. Good morning, all, and Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Offering my expression of gratitude to Allah Subhanahu wa Ta'ala due to His favor and charity, so we could meet together in visiting professor program today. The first, I'm thank to the Dean, Mr. Budiono, and then the speaker. At this time, Associate Prof. Chuang, Ting-Wu Chuang. Yeah, because because for taking time out of your professor busy schedule to attend in virtual this event. And then Bu Lintang be as moderator today. And also I thank to the committee who have organized this wonderful event. Student of epidemiology, our department. Also the all participants who have joining this meeting. Thank you. I would like to say that it is our privilege and a pleasure to have the great event held in our department, epidemiology and tropical disease. We have two interests in our department. One is epidemiology, and the other medical entomology. We often call in public health entomology. This event gives us a new issue about the vector-borne disease in the topic. About the epidemiology and also the risk forecasting. I think this topic is very important to our study and our research, so we can implement how to control this disease in our environment or communities. Yeah, and the participant in this virtual meeting are students, almost all the students of public health faculty, and also our lecturer who interested with the topic of epidemiology of vector-borne disease. Yeah, I already mentioned before that the participant almost from undergraduate and also postgraduate, especially in Magister Epidemiology. Yeah, I think it's not a long time to opening speech. Yeah, finally, I as a representative of the Epidemiology department, we hope all participants enjoy this scientific meeting and have any benefits to us. And we apologize if there is our shortcomings in the organization of this meeting. So, wassalamualaikum warahmatullahi wabarakatuh. Be back to the MC. Thank you.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Bu Martini, for the welcoming speech. And next, we would like to invite Mr. Budiono as the Dean of Faculty of Public Health at Diponegoro University to open this event. To Dr. Budiono, BSc MPH, please, this time is yours.
Lukman, your voice not clear? Yeah, maybe it's, yeah.
Sorry.
Harder. Yeah, the voice is not clear.
Wait a minute. Okay, thank you, Mrs. Martini, for the speech. And next up, we would like to invite Mr. Budiono as the Dean of Faculty of Public Health, Diponegoro University, to open this event. To Dr. Budiono, BSc MPH, please, the time is yours.
Lukman, maybe Mr. Budiono still any agenda because he is not attend in this event today, this morning. Maybe Mrs. Martini.
Okay. Yeah, we would like to invite Mrs. Martini to open this event. Once again, please.
Yeah, okay. Based on your permission, maybe, yeah. As possible, we open this agenda with say Bismillah together. Yeah. Bismillahirrahmanirrahim. Yeah, please enjoy this meeting. Thank you.
Okay, thank you, Ms. Martini. Dear participants, we are now about to start our main agenda. But before that, we would like to invite our moderator here to lead our discussion for the speaker's presentation. And today's discussion will be led by Mrs. Associate Professor Lintang Dian Saraswati, MPH Epidemiology. In case you haven't known her yet, we would like to show you her curriculum vitae first. Dear operator, please show us her CV.
Maybe Lukman. Okay. Your voice is still not clear, I think. Maybe you can load more.
Okay. Okay. Hello, test. Is it still unclear?
Okay, clear. You can repeat it.
All right. Okay. I think Mrs. Lintang is already here. Yeah. Can you hear us, Miss?
Yes.
Okay. Thank you. Yeah. Okay, Mrs. Lintang. To start discussion, this time is yours. Thank you.
Okay, thank you. Check, is my voice clear enough?
Yes, but like a doubling voice maybe.
Doubling voice?
Yeah, yeah.
Wait. I don't use any.
You can check your voice.
Clear?
First, yeah.
Lisa, can you hear me?
Yes.
Clear? Okay.
Little bit
better. Yeah.
Okay, thank you. Good morning, the Excellency, the Dean of Faculty of Public Health, Professor Diponegoro, Mr. Budiono, the Excellency Head of Bachelor Program, Mr. Zen Raffiuddin, the Excellency Head of Department of Epidemiology and Tropical Disease, Ms. Martini, colleague in Faculty of Public Health, Diponegoro University, and all ladies and gentlemen. Welcome to Visiting Professor Program. My name is Lintang Dian Saraswati. It is my pleasure to be a moderator for this program on Friday, September 10, 2021. Rule for this virtual meeting are: first, please mute your audio and turn on your webcam or video if applicable. Second, if there are any questions, you can ask in Q&A box or chat or using raise hand feature for direct conversation. Please mention your name, institution, and the question. First of all, may I briefly introduce to you our visiting professor from Department of Molecular Parasitology and Tropical Diseases, Center for International Tropical Medicine, College of Medicine, Taipei Medical University in Taipei, Taiwan. He graduated with PhD degree in epidemiology from Department of Epidemiology, School of Public Health, University of Michigan, USA. He got his master degree in epidemiology from Institute of Epidemiology, College of Public Health, National Taiwan University, Taipei, Taiwan. Some of his significant positions are in 2018 as Associate Professor in Department of Molecular Parasitology and Tropical Disease, Center for International Tropical Medicine, College of Medicine, Taipei Medical University, Taipei, Taiwan. And in 2009 until 2012, postdoctoral research scientist, Spatial Science Center of Excellence in South Dakota State University in USA. And 2007 until 2008, graduate student instructor, School of Public Health, University of Michigan, USA. 2004 until 2007, graduate student research assistant, School of Public Health, University of Michigan, USA. 2002 until 2003 as research assistant in Taiwan Public Health Association, Taipei, Taiwan. Some of his significant publications include 52 documents with index 17 in many areas of epidemiology. Recent publications in 2021 are long-term exposure to ozone and sulfur dioxide increases the incidence of type 2 diabetes mellitus among age 30 to 50 adult population, and also about effects of soil exposure and land use characteristic on neurodevelopment among children under 3 years of age in northern Taiwan. Ladies and gentlemen, please give warm welcome Professor Ting-Wu. Hello, Professor Chuang.
Yeah, I can hear you. Yeah, thanks for nice introduction. And so let me share my PowerPoint.
Yes, please, thank you.
Yes, can you see me in my PowerPoint?
Yes, I can see it.
Okay, great. So, hello everyone. My name is Ting-Wu, and actually I just met another Indonesia scholar yesterday. They are from Bandung. So that's another project involve the mosquito control and the GIS system establishment in Bandung. So I will cover some kind of idea in my talk today. So my title today is about the vector-borne disease, epidemiology, and risk forecasting. So I will give you an overview about how does the risk forecasting look like. And I will share some of my previous experience on different mosquito-borne disease and our work to forecasting the risk. So I will start from this very beautiful figure. This one is published by WHO. They talk about the world deadest animals. So you can see the number one is mosquito, which means the mosquito can kill more than 70 to 5,000 people per year because malaria. So I believe in Indonesia, you also have the outbreak for malaria in some place. And following by human, caused by war, okay? And for others, like the number three is snake bite. So the mosquito-borne disease is the top one. They kill many people every year. And we know for mosquito species, there are three major species can bring many different diseases. For example, the malaria can be bitten by the Anopheles gambia. So that's the major vector in Africa. But I believe in Indonesia, you have different vectors. And the Curious fasciitis is a vector for filariasis, right? And for Aedes aegypti, is a vector for dengue, Zika, and chikungunya. So the mosquito can carry a lot of different disease, and so the country in the tropical region will suffer from this burden of disease. So here's the global map to show the risk for two most important mosquito-borne disease in the world. The upper panel is malaria, and lower panel is dengue. So you can see the malaria is focused on Africa, right? Caused by Plasmodium falciparum. And in Southeast Asia and Latin America is caused by the Plasmodium vivax. But for dengue, you can see it's widely spread through the tropical and subtropical region worldwide. So these two mosquito-borne disease has become the very, very important infectious disease in the world, and it can cause a lot of disease burden. And right now we have the treatment for malaria, and we can say we have a vaccine for malaria, but it has not been distributed widely. But for dengue, we have no effective treatment, and we have no vaccine yet. Although there are some vaccine has under the clinical trial phase 3, but the vaccine trial encountered some issue. I will talk about the vaccine later. So you can see the dengue transmission, the burden of dengue become more and more severe comparing to malaria. Okay, and here are the list for some disease can be transmitted by mosquito. Although my title is about vector-borne disease, but today I will focus on mosquito. You probably know the vector can be referred to mosquito, tick, mite, or other insects. But today I will focus on mosquito only. So from this list, you can see malaria is caused by Plasmodium and transmitted by Anopheles species. And filariasis is caused by another parasite, and the disease is transmitted by Culex species. And for yellow fever, JEV, West Nile virus, dengue, chikungunya, and Zika, those are virus-related mosquito-borne disease and transmitted by, most of them transmitted by Aedes, in addition to JEV. The JEV is transmitted by Culex. And for these two, I highlight in green, we have vaccine. So these two diseases doesn't cause very severe burden worldwide, because if you have received vaccination, you can prevent the infection for yellow fever and JEV. However, you can see that those 4 different diseases here, West Nile virus, dengue, chikungunya, and Zika, are highlighted as blue. Currently, we don't have very effective treatment, and we don't have vaccine for this disease. So we only can do some prevention control work to reduce the disease incidence. I will talk about West Nile virus later, because it has become the most important mosquito-borne disease in the USA. But for people living in Asia, you're probably not very familiar with this virus, but we are very familiar with dengue, right? Dengue, chikungunya, and Zika. These 3 virus diseases in the recent year, we always talk them together, because those are transmitted by the same vector, Aedes aegypti and Aedes albopictus. So we have so many mosquito-borne disease. When we trace back to the history of those mosquito-borne disease, we can see those viruses, pathogen probably come from animal, come from forest. So if you check the textbook for dengue or other mosquito-borne disease, they will definitely mention about the zoonotic cycle, the virus transmission between mosquito and monkey in the forest. And someday, some people living in the zone of the forest maybe get the virus, encounter the vector in the forest. And then with the population growth and urbanization, the virus can bring from forest to human and establish a new cycle in urban. So right now we are talking about the transmission cycle in urban. So it can be, like for dengue, it's composed by Aedes aegypti and Aedes albopictus, and transmit the virus from human to vector. But if you go back to the forest level, you will see different vector. But right now we only focus on this part, the urban part. We don't care about the transmission in the forest. So that's the some kind of history, the evolution history of many mosquito-borne disease, especially for dengue. So here comes arise another issue we call One Health. I think for the people from public health and epidemiology, the One Health idea is very, very important, especially we are suffering from the COVID-19, and you probably know the virus come from animal. So what does the One Health mean? The One Health means we should cooperate with the people, not only from human health, but also from animal health and environment. So we compose these 3 components, and that is the idea of One Health. We need a collaboration among the human health, animal health, and environment. So here's the basic idea for the transmission from animal to human population. So I won't go over the very detailed, because it involves some mathematical modeling approach. You can see the SEIR. I'm not sure in your program, did you talking about the infectious disease modeling framework? The SEIR means the susceptible and exposure, infected, and recover. The 4 different ideas, and represent 4 different group people. So when the pathogen enter a community, the people in the community are susceptible to the virus or the pathogen. And then you expose. Somebody might expose to the transmission. And among this group of people, some of them will get infected and then recover. But for some diseases, probably no recover. Okay, so that's the idea for mathematical modeling. And so this one can involve pathogen, vector, and also spill over to human population. So right now we are encountered to a very, very complicated system. We are not dealing with the pathogen only happen in human, but also the spillover from animal. Okay, so let's go back to the mosquito. I believe most of you know the life cycle of mosquito. This one is the example for Aedes, but it's quite similar for Culex and Anopheles. The difference only for the morphology. The morphology of different species are different, but the life cycle will be very similar. So the mosquito life cycle, they need water. So they lay the egg in the water, and then the larvae will hatch from the egg and they survive in the water. And after the 4-star stage, the larvae will convert to pupa. Okay. And then about after 2 or 5 days, the pupa will convert to adult mosquito. And when the adult mosquito looking for the bird meal, the female mosquito looking for bird meal, and when they finish the bird meal, they need to find a place to lay the egg. So the place will be somewhere have water. So that's the life cycle. In general, to finish the one life cycle, it takes about 25 days under temperature about 25 degrees. Okay, but if the temperature higher, they will shorten the life cycle. So that's why in many risk forecasting model, temperature is a very important trigger to enhance the risk probability, because the higher temperature can shorten life cycle and also shorten the EIP. I will talk about EIP later. EIP is intrinsic incubation period. That means the virus stay in the mosquito body and make the mosquito become infectious. It also takes time. So the higher temperature can shorten both the life cycle and EIP. So also enhance the transmission probability. And another very important factor for the climate aspect is rainfall, because the rainfall create a lot of water site, but different mosquito species have different preference for their habitat. Like for Aedes, they like the artificial container. So if in your environment you have many artificial container, when the rainfall coming, those container will fulfill water. So that will become a very good place for the mosquito to lay the egg. But the behavior for the egg laying also different among different species. So I won't talk too much about this. So you just need to understand how does the climate, the temperature, rainfall can affect the life cycle of mosquito and also can affect the propagation rate for virus. So here's the basic idea for the impact for macro environment on VBD. Okay, we talk about macro environment because today we are talking about the risk forecasting. We try to use different environmental parameters to forecast the transmission risk. For the micro environment, let's talk about the pathogenesis, immunity in human, and how does the virus, how does our immune system fight with the virus? So it's out of our scope today. Okay, so when we talk about the macro environment on VBD, we need to show that this triangle. You're probably very familiar with this triangle, right? It's a vector, mosquito vector, dengue virus, or you can say it's other pathogen, malaria or chikungunya and Zika virus. They are quite similar and host the human people. And what kind of factor can affect this triangle? When we talk about the host and virus, it's quite simple. It's at the individual level stage. So some people, when they get infection, they have symptoms, and other people, they don't have symptoms. So that's the very general situation for many infectious disease. You have people have symptoms about 20%, and about 80% you got infection, but we don't have any symptom. So it's relevant to your immunity. And for dengue, if you want to mention some idea about herd immunity, that will be very complicated I believe you are from public health, so you should know the idea of herd immunity, right? In the population, if more people get immune, you can protect for other people. They don't have immunity to some pathogen. But for dengue, the herd immunity is very complicated because we have 4 different virus types for dengue. And if some people infect dengue once, and after a couple of years, you are infected by other type of virus, the immunity doesn't help. It also can give you some worse condition. You enhance the probability to have severe dengue. So the herd immunity for dengue transmission is not so straightforward, okay? But for short term, yes, if the big outbreak occur, the population can establish about herd immunity for less than 1 year. For the 1 year, probably the infected people, they can resistant to the infection for dengue. But after 1 year, the situation become more complicated if we infected by the different type of dengue virus. Okay, that's the case for dengue. And how about the vector and host? The interaction between vector and host is relevant to some kind of sociological or anthropological factors. So that means the people movement and the interaction between people, the travel pattern for people can affect a different interaction between mosquito and host. For instance, if you live in an urban region and you travel a lot, so you have a higher chance to contact vector if the vector insists in stay in the urban region. And this one is not very easy to monitor. So some study they published recently, they use the cell phone. Okay, the cell phone to chase your movement. Like the one study in Pakistan, they use a cell phone to chase people movement and to link the risk between people and mosquito vector and the dengue cases. Okay. And the third part is the interaction between mosquito vector and virus or pathogen is environmental drivers. Because we are talking about mosquito-borne disease. Mosquito is an insect. So the life cycle for insect is highly affected by different environmental conditions, including climate. Like I mentioned before, climate, the temperature, rainfall, humidity, and also the different land cover land use. Because the mosquito, they choose different habitat based on the different land cover land use. Okay, so this kind of environmental driver can have the effect on the interaction between vector and dengue. So when the environmental driver is appropriate for the mosquito survive or the virus propagation, you will enhance the transmission probability. So here in the middle, in the center is we call about some factor affect the vector and dengue virus and also the host is the vector abundance. You have many mosquito, of course, the risk is higher. And the EIP, I just talked about this term before, right? The intrinsic incubation period. That means when the mosquito infected by the virus, at that time, the mosquito is infected, but not infectious. So it will take about 10 to 14 days to make the mosquito become infectious. So the EIP also can be affected by temperature. Higher temperature will shorten the EIP. So that means when the mosquito biting a people, if the temperature is 35 degrees C, the mosquito can become infectious in 1 week. Okay, and also contact probability. The people contact to mosquito, so it's allow the transmission occur. So this triangle is very important to when we talk about the macro environment on VBD. And today I will focus my talk in this part, the environmental drivers on the mosquito abundance and the transmission. And here is the experiment has been conducted by the professor from UC Davis. His name is Bill Risen. He's very, very famous, is a very outstanding scientist to study mosquito-borne disease. And so when the West Nile virus outbreak occurred in the US, so in his lab, he tried to understand how does the temperature affect the EIP. So you can see the x-axis is temperature from 10 degrees C to 3 degrees C, and the y-axis is EIP. So, and this one, the number is the risk level. So you can see when the temperature going higher, and the EIP, which means the period from infected to infectious, shorten from about 30 days to 6 days when the temperature go to 30 degrees C. Of course, this one is the experiment, the test in one university, but overall, it's the pattern can be applied in the field. But the difference is the temperature and the day of EIP are different in different species. But it's very straightforward that when temperature higher, the EIP becomes shortened, so the transmission risk becomes higher. So that's the very, very important evidence to show the interaction between temperature and mosquito ecology. And this one is another very important but very interesting study. It's been done by Professor Erin. She's the professor from Stanford. Their topic is about the thermal biology of mosquito-borne disease. Because we know the temperature have very high, it's very important to trigger, to shorten the EIP and to shorten life cycle. But we have a lot of different mosquito species with many different disease, right? So are they the same? The results show you they are not the same. So you can see there are a lot of different color here, right? So that those different color indicate different disease transmitted by different mosquito. Okay, so you don't need to go over it one by one. You just can see here in the bottom, dengue virus caused by Aedes aegypti, and the green one, Plasmodium falciparum, is malaria pathogen transmitted by Anopheles. So they use the mathematical model to show the niche of the temperature. So you can see the green line is here, it's for malaria. So that means their temperature niche is probably from 18 degrees C to 30 degrees C. But if you check the dengue virus, the purple one, the niche is from about 23 degrees C to 35. So that means the Aedes mosquito can tolerate higher temperature than Anopheles species. So in this case, the author suggests that because we are suffering the climate change, right? So we have very hot season like this year. So when the temperature, the global temperature become higher, the probably trigger the transmission for dengue. And for the Anopheles, for the malaria, probably can be decreased by the higher temperature. Here we talk about extremely higher temperature. So it's quite interesting. So you can think about when we're facing the rising temperature globally. So in next 20 years, 50 years, probably dengue will become more and more important than malaria. Malaria transmission might be reduced due to the very high temperature. But you can see that Aedes aegypti can tolerate higher temperature. So this one is a very interesting study they published on Ecology Letters. It allowed us to think, even though we talk about mosquito, but different mosquitoes still have different features. Okay, especially for the tolerance for temperature. And here's another very important idea for mosquito-borne disease epidemiology. This one is talking about the transmission dynamics and the population structure for vector. So here you can see, you can check this, the picture. Let me explain clearly. The blue one, blue mosquito is nulliparous, which means it's the mosquito just hatched from egg. So it's quite clean. It's no infection, okay? And the people in green is healthy people. So this one is susceptible people. And the red one is people who get infection. Let's say this one is dengue patient. And when the mosquito biting these people, it's fine. The mosquito still clean, okay? They're still susceptible. But if the mosquito biting this person, okay, they get infected. Remember, I talked about infected mosquito is different to infectious. So when they're biting this person, the mosquito retrieve the virus from this person. And so at this stage, we call them infected. But in this stage, if the mosquito goes into biting other people, there's no risk for transmission. They need to waiting for about 10 to 14 days, the mosquito become infectious. So for this mosquito, it's dangerous. It can transmit the virus to other people. So this paper, they do the experiment in the field. They try to collect different stage of mosquito in the field. You can see most of the mosquito are susceptible. If you can see the compare the color, and the blue one indicates the newborn mosquito. But for infected or infectious, actually the proportion of this mosquito is very, very low. So this one is just echo to our previous experience. If you want to go to field to survey the infected mosquito, it's not very easy. If you are working on West Nile virus, it's probably okay. You can collect some proportion of mosquito get infected. But if we are focused on the dengue virus, on the dengue transmission, it's not very easy to capture the Aedes aegypti in the field and get infected. So you can see the proportion is very, very low, but the transmission still occur among population. So it just gives you an overall idea that even in the field, even for the mosquito, they have a different structural population. Some of them are non-infected, and some of them are infected, and some of them are infectious. Okay, so that's the basic idea for the mosquito-borne disease. So let's start from my first example, the West Nile virus. The West Nile virus was first identified in Africa, in Uganda, from a woman. He got fever, and she go to the clinics, and then the physician identified, okay, there's a new virus called West Nile virus. But during that time, the West Nile virus doesn't cause very severe disease outcome. The woman just have some kind of flu-like syndrome. And in fact, the West Nile virus infected person, 80% of them, they don't have any symptom. The only 20% can have flu-like syndrome. So you probably can recover in 1 week. But about 1% of people infected by West Nile virus, they can develop to a very severe neuroinvasive disease called WND. And this kind of disease outcome is not easy to recover comprehensively. So some people they got WND, they also have some memory issue. They also have some muscle problem. Okay, and currently we don't have vaccine. We don't have treatment for this disease. And when this disease attacked USA in 1999, it first arrived in New York City. So in that year, many people observe one phenomena. They see a lot of crow die. The crow, like this bird, okay, American crow, it's everywhere in the US. And because the West Nile virus can infect many different avian species, about more than 300 avian species can be infected by the virus. The birds is the natural reservoir for West Nile virus. So in nature, the virus is transmitted between mosquito and birds. And human and horse are, we call it dead-end host, which means no human-to-human transmission. So this idea is very different to dengue, right? Dengue, we know it can transmit from human to human by mosquito biting. But for West Nile virus, if a person is infected by West Nile virus, because the viremia is very low, so when the mosquito biting this person, there's no chance for the mosquito transmit the virus to other person. So there's no human-to-human transmission for West Nile virus. And the same idea for the horse, because this virus also can infect horse and to cause horse sick. And the West Nile virus can be transmitted by many different mosquito species. Culex are the key vector, but it also can transmit by Aedes and also Anopheles. So in the CDC laboratory, they have to do an experiment to show, okay, at least more than 60 species of the mosquito can transmit West Nile virus. Okay. So when the virus attacked US, they noticed the birds population decreased in some place because this one, the new virus arrived in North America. So it's caused a high fertility rate for some species of birds, especially for Kobe species. Like this one is the blue jay, and this one is crow. So the high mortality rate among these two birds. So about from 1999 to 2003, you can see some people like to report dead birds near their garden. So in the early stage of the transmission, some health department, they ask people to reporting dead birds. They use the dead birds as the early warning sign. But you know, this kind of reporting system will become useless from after about 5 years because people lose the interest. The people get used to the virus, so they don't report the birds anymore. Okay, so the virus affects birds a lot. So some people start to study what kind of birds is a super carrier for the virus, and they identify one species called American robin. This bird is everywhere in the community of the US city, and the birds can carry medium level of viremia, but because the birds living very close to human, so when the mosquito biting the birds, there's a very high chance for the same mosquito to biting people. So the virus can get from the birds and infect the mosquito, and the curious species can biting people nearby. So that's how does the transmission occur. Here's the vector, those non-virus vector distributed in the US. So you can see it's everywhere, but actually in different areas, the vectors are different. Like in the western part, in the eastern part, the curious pipian is the main vector. But if you go to the central part, the curious tarsellus become the main vector. And if you go to the western part or southern part, the curious concaphasiatus become the main vector. So the different area have different vector. That means the ecology of mosquito also different. Okay. So when the West Nile virus transmission occurred in the US, then many people start to study mosquito. So to study mosquito, you need to capture them, because we know why do we need to capture mosquito? There's a two purpose. The one purpose is to understand the abundance, the population of mosquito in the certain area. The second purpose is to test the infection rate for mosquito. So for this kind of disease is transmitted by Culex species. It's easier to test the infection rate because you can capture more than 1,000 mosquitoes per night. The Culex species is a very, very huge population. So you can, using the mosquito trap like this one, we call CDC CO2 light trap. You set up a trap in the field and you can monitor the mosquito population. And then we bring the mosquito sample back to your laboratory. You can testing the infection rate. So that's the index called minimum infection rate is to refer to the mosquito infection for West Nile virus. And these are the 4 different species in the US which can transmit West Nile virus. Okay, and here are the different traps for vector surveillance. Like this one, just show you on the previous slide, we call CO2 light trap. You put a light on the trap and connect to CO2 tank. So this kind of trap can attract mosquito the activity at night, because the mosquito can attract by the light and CO2. And this one we call BG trap. This one is designed for capture Aedes. You know, the activity of Aedes is during daytime, especially for Aedes aegypti and Aedes albopictus. So the BG trap, they contain a chemical compound in this trap. The chemical compound is mimic our odor of our skin. So they can attract the mosquito come in the trap, and then there's a fan in the trap can suction the mosquito. So these two trap is designed to attract we call host-seeking female mosquito. So the meaning for epidemiology is very important here is they are tracking the host-seeking mosquito. The host-seeking mosquito indicate the probability of transmission risk. If the female mosquito is infectious and they are looking for blood meal, looking for people. So if we have more mosquito captured by the trap in certain place, that means the transmission risk become higher. And there's another two trap here. One is called gravity trap. The other one is called OV trap. These two traps are designed to capture the gravity female. What does a gravity female mean? The gravity female is the female took blood meal, and then they are looking for the place to lay the egg. So these two traps have different meaning in epidemiology. That means the mosquito, the gravity female, they don't looking for the blood meal anymore. When the female gravid, they have no interest to take blood meal. So in this stage, they are looking for a place to lay the egg. So for gravity trap, they put haze in this tank, and they will attract female mosquito, gravity female mosquito to lay egg. And there's a suction device here. So they will collect the gravity female. So you can collect the mosquito back to your laboratory to testing the infection rate. And this one is OV trap. OV trap is a trap that's very easy to operate because they just use the black cup, and then it's attract female mosquito to lay the egg. So the people can bring the cup back to laboratory to counting the number of the egg, and you also can hatch the egg in the laboratory. So this one is much easy to operate. So right now in Taiwan, actually the health department, they put a lot of OV trap in the field to monitor the mosquito population. And also the OV trap have one benefit. If you put many OV trap, you can reduce the population number of a mosquito in the area. Okay, so those traps have different function and different meaning in epidemiology. So when you talk about the trap, okay, you put a lot of different trap in your place, and when you bring those data back to your lab, so how to analyze those data? So we're talking about the spatial epidemiology. You probably have heard this term before. Simply speaking, the spatial epidemiology is we try to include the spatial component in our analysis. Before the GIS technique become very mature, I think in the Epid study, we usually design like a case control study, cohort study, and or the time series study. There's no spatial component in the classical Epid design. But when we can use the GIS technique, we can visualize our data in space. Like this, we can use the technique. Right now, we have some free software. Also, we have commercial software can operate the spatial data. So you can put the surveillance site. If you put the 30 mosquito trap in your study area, and you can put the location information in the GIS software, then you can visualize, okay, these are our mosquito site. And you also can visualize the mosquito index. And then you can go further to conduct some model to forecast the risk. Okay, so here I just talk about a little bit about the spatial epidemiology and how to use GIS. Actually, the spatial epidemiology is a very old idea. You probably know John Snow, right? The cholera map they did in London in 1854. And during that time, we don't know the cholera is transmitted by the bacteria. Okay, the pathogen has been identified in 1884. So during that time, the John Snow, he doesn't know the pathogen, but he only know some people have diarrhea. So he used the dot to indicate the patient. And then they identify, okay, those patients are living very close to the water pump. The water pump is supported by the one water company, water factory. And so he guessed, okay, probably the water is contaminated. So this kind of John Snow's map is the very early map he did, and he did by hand. But right now we can did by computer software. So this one is an example. This area is Tainan City, and the red dot is the site for mosquito surveillance. So the people, the health department people, will go to this village to do the surveillance for mosquito vector, and they can calculate the house index, container index, and brutal index. Those indexes are very common used for monitoring the dengue transmission. So you have those sites, so you can retrieve the coordinate information, latitude and longitude. So you can put this information on the map, and you can show at the village level what does the brutal index look like. So here you can see, if you convert those point data to polygon data, you can see some village have higher BI. So when you have higher BI, you probably can do some action. You can go to this village to do intervention, to spray the insecticide, or to do the community education to reduce the transmission risk. Okay, and so to visualize the vector index is the very basic one, and then you can do something. You can detect hotspot. So here they show the statistically significant hotspot in the study area. So you can see the red village indicate this one is the major hotspot. How to do it? Currently, we have many very easy to use spatial statistical analysis like local Morris eye, GetSG, and scan statistics. This method is widely available in most of the software. So you can do a test to detect the major hotspot or cold spot in the area. And then this area becomes your focus. Okay, you can enhance your intervention measurement, control measurement in this place. And if you want to do some prediction, you can using the method we call interpolation technique. Like this one, we only survey the mosquito species, the vector index in some place. But if you want to predict for the whole study area, you can use either IDW or kriging. Those are different mathematical methods embedded in the software, and you can do the whole region interpolation. Okay, but you must be cautious because different methods have different assumption and limitation. Like IDW is based on the distance, so give the different weighting for different distance. But this one allow you. Actually it's a research-oriented method, so you can do the prediction for the hosted area. And this one is only for one single variable. If you want to do the bivarial analysis, like here, you also can show, okay, I want to compare the BI, the brutal index, and the dengue transmission. So you can see the brown color here indicate that in that village is high BI and high dengue incidence. So you can try to figure out, okay, the brown area is high for both index, and what's going on there? And on the other hand, some area is very high BI but low dengue incidence. It's very common for the dengue transmission in many different areas. We have a high BI, high vector index, but the dengue transmission is very low. So you also can try to understand what's going on in that place. So this kind of visualization approach can help us to understand the distribution of disease and distribution of vector population very well. And you can get some insight from this visualization work. Okay. And then how to expand this work to forecasting. This one is the overarching hypothesis for the forecasting work. This one is the vector ecosystem, right? The interaction between mosquito population and pathogen. Like for dengue, it's the Aedes aegypti and dengue virus. And we care about the transmission from mosquito to human. And how to predict the transmission risk. We can utilize the different environmental driver to predict mosquito population and also predict to human disease because they are correlated. And in general, we think about, okay, if we want to use the environmental driver to predict mosquito population, we can use in the weather station and you can collect the temperature, rainfall, humidity from weather station. That's true, okay? But the weather station data is not always available. For instance, in the rural region, you probably doesn't have any weather station. And in urban region, you probably have more, but some weather station might have many missing data. The maintenance issue is also a problem. So when we conduct many forecasting model, either in the US or in the developing country like in Africa, to collect comprehensive environmental data is always a problem because we are not able to rely on the weather station. Like we have conducted some study, malaria study in Ethiopia. The Ethiopia doesn't have any weather station. So we probably have no way to retrieve those environmental variables. But fortunately, we have one very useful weapon, remote sensing, the satellite. Currently, we have many satellites above our head. And different satellites have different sensors. So the sensor can capture the information on the Earth, and we can derive those information to different environmental variables. And those variables can play as the proxy for the local condition. I need to highlight here is the variable captured by remote sensing data is not the same thing we capture by the weather station, but that's the very good proxy. They have very high correlation. That means the weather station measure temperature. We call air temperature, about 2 meters. But the satellite images can give us the temperature index we call land surface temperature. But land surface temperature is not equal to air temperature, but the pattern is highly correlated. So that's very important. So we always say the variables derived from satellite images are the proxy for the local environment. So based on this kind of idea, we can try to use the remote sensing data to be a proxy for local environment change, and then to predict mosquito population and also predict human risk. Okay, so that's the overarching hypothesis. So here is just a figure to show the Earth observation satellite. We have a lot of them above our head, but the issue is how to use those data. Okay, it's another technical barrier for people working in public health. Okay, so currently we are in the area is the transdisciplinary collaboration. We need to collaborate with many scientists in different fields. So here is the basic idea for remote sensing data. This one is a satellite, and this one is the sun. So the sun can have a light on our Earth, and the reflection can be detected by the sensor on the satellite. The people on the ground can try to retrieve those information and process the information. And we are the people in this stage. We don't need to care about how do they retrieve the information, how do they operate a satellite. And we also don't need to do the data quality processing. We only need to use their product. They can produce many different products. So those products can refer to land cover, land use, the land surface temperature, and the vegetation index and rainfall. So we can use those data in our analysis. And this one is a basic idea of how the sensor can tell us, why the sensor can differentiate different land cover, land use. That means this one is our Earth's surface. So there are forest, water, grass, and bare soil or building area. The different land coverage type, they have a different reflection energy. So when a sensor receives those energy, they can differentiate, okay, this one probably come from urban region. This one come from forest land cover. And this message come from water body. And if the sensor also cover the thermal band, it can calculate the temperature index. Okay, so that's the basic idea for why the satellite image can give us different environmental conditions. So this is the basic idea for the hygrometric evaluation. The most of the sensor on the satellite can cover this range of the wavelengths. Okay, this one is a visible spectrum. It's from 0.5 micrometer to 0.7 micrometer. If a sensor covers stage, you can see the land cover and land use. And if the sensor covers thermal infrared, they can retrieve the temperature. And if the sensor covers microwave, you can retrieve the rainfall data. So right now, this kind of data is available everywhere, but the issue is how to select appropriate one and how to process them, because the remote sensing data is not like a Excel file. They give you the image, so you need to know how to convert the image to the data. Like this one show the different land cover, land use have different reflection pattern, so you can differentiate. Okay, this one's water, and this one is indoor forest. This one is grassland. So about a couple years ago, we tried to use one satellite sensor to capture the temperature, vegetation index, and rainfall to develop a model to forecast the distribution of mosquito population. So this one is our forecasting result. We forecast 2 different mosquitoes, Aedes vexans and Cus tarsalis. So you can see this kind of forecasting tell us the different temporal and spatial pattern for the 2 species. Like Aedes vexans emerged earlier in week 20, and the population dominated in this place. And for this species, it emerged lately in week 26, and their spatial distribution is a little different comparing to Aedes vexans. So in the last 10 or 20 years, more and more people start to using different satellite images to do the ecology study or to do the risk forecasting. So this one is for risk forecasting. We forecast the West Nile virus incidence in the US. This one is the central part of US. And in the model, we're including the temperature, vegetation index, and evaporation index to predict the risk for transmission in different years. So you can see the prediction show the different level of risk in different years. Okay, and this one is the comparing to the predict value and observed value. So they have very consistent linear pattern. And after we developed the model, we set up a model. We collaborate with the Department of Health. So right now in the state called South Dakota, that Department of Health have a meter. The meter show the risk level for West Nile virus transmission in the state is low or moderate or outbreak. So this meter is based on the model we have developed. We use the environmental condition in June to predict the outbreak level in summer. like in August, September, October, because that one is the peak level for the West Nile virus transmission. So in June, you probably can see, okay, in 2014, the risk is moderate. And we also can highlight where is the high risk region. So you can put a limited resource in this county to enhance their control measurement. So that's the basic idea for the forecasting model, and how can we act based on the output for forecasting model. It gives you some direction. Okay, this place should have more intervention intensity and put more effort there. Okay, so let's go back to dengue. So that's the West Nile virus, and then you can see I just used this case to introduce like the GIS technique and other method to and remote sensing to develop model. And I think we are more care about dengue virus because dengue is nearby, no matter in Indonesia or Taiwan, and we have very huge outbreak in 2014 and 2015. And dengue virus is RNA virus, and so it belong to the same family with the JEV, West Nile virus, and yellow fever. And this virus is transmitted by the Aedes albopictus and Aedes aegypti. And Aedes aegypti is the main vector because it's indoor mosquito and it's also dominant in tropical region. And like in Taiwan, we also have Aedes albopictus. So the Aedes albopictus is outdoor mosquito. So these two mosquitoes might play different role on the transmission. And we know there are 4 different serotypes, right? Dengue 1 to dengue 4. Although in 2015, there's a dengue 5, serotype 5 has been discovered in Thailand. But right now, we still say there are 4 different serotypes. And for the clinical outcome, it's quite similar to the West Nile virus. The most people doesn't have any symptoms, or only have the flu-like symptom. And very few people have severe outcome. If we don't treat properly, the mortality rate could be higher than 20%, especially for children or young infant. And for the severe dengue outcome, with the 2 clinical names for them, DHF and DSS, that's referred to the severe dengue clinical outcome. And currently, there are still some debate of the occurrence for DHF and DSS. Some scientists think about it's induced by the ADE, the antibody-dependent enhancement. That's you require the secondary infection. The first infection, when you infect by a certain type of virus, and after a couple of years, you infect by different types, you might cause the very severe ADE and to cause DSS or DHF. But there's also another scientist, they argue about it's probably due to a different virulence variation. Because in Thailand, they also identify some newborn child. They have never infected by the dengue virus, but also can have DHF and DSS. So right now, there's a 2 argument for this, the cause for DHS and DHF and DSS. And you can see the history of dengue. The dengue become more and more severe. It's from 1980 to 1989. And this one is from 1990 to 1989. So you can see in the past 20 years, the dengue has become a more severe issue in Southeast Asia and Latin America. So although the dengue virus is still in the list of the NTD, neglected tropical disease, but I think somebody started talking about probably the dengue is not NTD anymore. It's like a malaria, also a very important mosquito-borne disease. Okay, so this one is the case for the dengue fever. And in 2009, the WHO have changed the criteria for the severe dengue. They don't use the DHF and DSS anymore because there are too many non-standard clinical outcomes. So right now, if you have severe plasma leakage, severe hemorrhage, severe organ impairment, we all define you as a severe dengue. So keep the symptoms simple. And those are criteria for severe dengue. So they change the criteria. So you probably won't see the DHF and DSS very often in the future. Okay. And those are the 2 main vectors. For the dengue, this one tell you the viremia. This is very important for the dengue epidemiology. The viremia means when you're infected by the dengue virus, and you also can transmit the virus to other people if you're bitten by a mosquito. So the viremia occur 1 day before your symptom occur, and 5 days after your symptom occur. So 1 day before and 5 days after. So during this stage, it's the viremia stage. That means in this stage, you are able to transmit the virus to other people if you're bitten by a mosquito. Okay, and so some mathematician can using this kind of idea to calculate the transmission probability or the R0 reproduction number to show the dengue transmission. Okay, and this one is for diagnostic. Probably already know this. We can test using IgM, IgG, using ELISA, or you have an Enzo rapid test. This one has been applied in Taiwan in 2015, and like our meeting yesterday in Bandung, they also start to use Enzo rapid test for diagnostic because it's very quick, and also you can use the PCR to testing the nucleotide. Currently, we have some vaccine available, but it's not okay to be used widely. This one is called dengue vaccine. This vaccine has been conducted in Philippines, but they stopped the trial because they noticed the young children, the risk of young children become higher if you inject the vaccine. So right now the criteria, the recommendation for this vaccine is for the children older than 9, and the adult you have infected by dengue before. That's the assumption. The vaccine only can give to the population you have infected by dengue once. And why? Because they noticed in Philippines trial, the young children younger than 9, they probably have less chance to infect by dengue. When they receive the vaccine, they notice the mortality rate become higher when they infected by dengue again. So that vaccine has been halted in Philippines. Right now, it can be used. So in the USA, they also have a recommendation for this vaccine, but it should be keep in mind that this one cannot be given to the person who's never infected by dengue. Okay, and here are some control strategy in Taiwan. Actually, the dengue is the class 2, so the physician need to reporting to the CDC in 24 hours. And when we identify the community cases, we do actually we have a regular survey for mosquito index, and then if the index higher, the people will go to community to spread insecticide. And we also can do the serological test for the community to monitor the transmission. And here's the same, if we want to conduct the forecasting model for dengue, we also need to understand the interaction between climate and dengue. So this one is from a review paper. It talks about how does the temperature affect the mosquito development, also can affect survival and production, and also affect the virus replication and transmission. If you are interested, you can go to check this review paper. And rainfall also another important factor can affect habitat. Okay, so this is our previous work. We know we have a very huge outbreak in 2014 and 2015. We don't know why, because you can see this one is the time series pattern in the panel C. This is the dengue incidence from 1998 to 2015. So you can see before 2014, we usually have the case less than 1,000. In some year, only have 100, 200. But in 2014 and 2015, in these 2 years, we have more than 40,000. So it's very, very huge outbreaks. So it's occurred in Kaohsiung and Tainan, the southern part of Taiwan. And during that time, the case number is over our capacity of hospital. So it's a very big problem. So we try to understand what's going on in these 2 years. So we developed a model called DONM. This model will help us to identify the nonlinear pattern for the climate factor to affect the dengue transmission. So we had identified a model including the minimum temperature and rainfall. We also noticed that the temperature in Taiwan in 2014 and 2015, we have an extremely high temperature in June. So that's the main trigger, and trigger the mosquito population become larger and then to cause the outbreaks. So this one can have very good prediction to forecast the risk in 2014 and 2015. And we also step further to understand why the 2015, the temperature in this year is pretty high. So we link to the idea to the we call regional climate phenomena, the El Nino effect and La Nina effect. Okay. So I can show you the Enzo effect. You probably heard about the global climate change, heard about the Enzo. The Enzo is a regional climate phenomena. When the Enzo event occur, it can cause either high temperature or high rainfall or drought in different places. And in Taiwan, the Enzo can trigger the very high temperature. So you can see this one is in 2015. So you can see that in this area, it's become very red after July. So in 2015, it's a very strong Enzo year. And at the same year, we can see many dengue outbreaks in many different countries. So that Taiwan also affected by this effect. And we can apply the analysis called wavelet analysis to link the Enzo and dengue. So you can see red area indicated very high correlation between Enzo and dengue. So this year is 2015. Okay. And there's another, the right-hand side is another indicator for regional phenomena called IOD, Indian Ocean Dipole. I believe this indicator might be more important in Indonesia because it's the Enzo effect on Indian Ocean. But in Taiwan, we didn't see a very strong correlation between IOD and dengue. Okay. And also for the urbanization, we also try to figure out how this land coverage type can affect mosquito transmission and can affect dengue. So this case is in Tainan City, and we use the satellite images to differentiate 6 different land types, like a residential area, business district, recreation area, agricultural, wetland, and water body. So here is the outbreak in 2015. In this year in Tainan City, a very, very huge outbreaks. So you can see a temporal pattern from July to October. The outbreak occurred in this area called North region and expanding to the south and then to the surrounding region. So you can very clear to see the patterns from north to south. But in this region, we usually don't have very big outbreak. So it's very weird. So when we try to use the model to identify the high-risk land cover types, we notice the research area is a very high risk factor for the dengue transmission. And wetland is a negative impact. The higher wetland and lower transmission is not surprising. And for the research area, it's also not surprising. But the interesting thing is the pattern is not linear. That means if the percentage of the research area in the study region, about 40%, the risk is higher. But if the percentage of the research area going to high, we didn't see the risk become higher. So that's we indicated the nonlinear pattern. So you can focus on the area that the research area around 40%. That's the major hotspot for dengue transmission. Okay. And at the same time, we also set up a mosquito trap in Kaohsiung region, and we try to monitor the micro climate factor on the transmission. But this one is a little complicated because we use a model called kurtosis to evaluate the extreme temperature and rainfall. How does this effect can interact with the Aedes aegypti and Virus concaficiatus. So I want to skip this one because it's a little messy. I just want to show you the kurtosis. You can think about kurtosis is the idea about the anomaly of temperature, the pretty high or pretty low, and also anomaly of rainfall. So we can see both the Aedes aegypti, they are very sensitive to the kurtosis of temperature. So that means if the temperature going very high, it might trigger the population for Aedes aegypti. But it's only the pilot study, so we still try to figure out what is the detail, how does the extremely rainfall and temperature to affect the population of Aedes aegypti. Okay, so that's our previous work, and here's how our ongoing work. So we use many variables derived from satellite images, but we also noticed one problem is if the people working in public health, you probably no idea how to access the satellite images. You don't know how to process them. So we try to build an automated system to retrieve those environmental drivers from satellite images. So that's the first stage we want to develop. And second is we try to adopt the more advanced machine learning or AI approach to develop a forecasting model. So here's a framework of our system right now. We call them RSEPPH, the remotely sensed environmental parameters for public health. So we use the platform supported by Google called GE, the Google Earth Engine. The GE platform, they have a lot of images, but the issue is you need to know how to write a code to retrieve the image and process the image. So we try to build this platform. We can develop a Python code or JavaScript to process the image automatically. So you don't need to understand what kind of image I need to use. You just need to send a request. Oh, I want to have the vegetation index. I want to have the rainfall data. I want to have the temperature data in which place. And then this system can automatically process for you. And then you can combine your data from your public health system, from your surveillance system. For example, avian influenza, dengue, or other disease. You use your own data set and then try to develop different model. So we also prepare some template of model, like random forest or the logistic model for you to embed your data and then combine these two data set and to do the forecasting and also for visualization. So this one is under development, and currently we are in this stage. We try to develop different Python code to retrieve those different satellite images and calculate the different index. So you can see this is a temporary achievement, or you can focus on Southeast Asia. So the purple color indicate the temperature data from satellite images. So if you want to ask me to calculate the temperature for the year 2000 to year 2020, it's okay, because the satellite image you can trace back to year 2000. So you can have the time series data for temperature that's for every week or every month. So this kind of system can give you very comprehensively environmental parameters, and then you can use this data for your analysis. So I think I need to stop here. I talked a lot of things. I guess probably some of you may not be digest very well. So I'm very happy to take any question from the audience. Thank you very much.
Okay, thank you, Professor Chuang. Okay, is there any? That's a very interesting talk. Now, if anyone has any question, I'm sure Professor Chuang will be pleased to answer them. Is there any? Perhaps you can write it in chat box, or you can ask in Bahasa, and I can try to translate it, or you can use the feature of raise hand. So wait, I check the gallery now. From student, from Diponegoro University, from colleague. or other university? I see there's a Miss Misna in here and your student. Oh, thank you, Miss Misna. Okay, Professor Chuang, Miss Misna want to ask about what diseases are within the scope of vector surveillance in Taiwan and how effective is the implementation of vector surveillance in Taiwan in controlling dengue fever? What are the indicators used to assess this? Thank you.
Okay. Actually, we only monitor dengue because in Taiwan, the dengue is the most important mosquito-borne disease. In addition to dengue, we also have JEV, Japanese encephalitis virus, but we have the vaccination for the people. So we don't monitor the vector for JEV because the case is very, very low. Every year, probably only have 10 or 20. And so the dengue is a major one. So all the health department in Taiwan, they focus on dengue. They are doing the regular surveillance, vector surveillance in most of the city, especially in Tainan and Kaohsiung, the two major hotspots. So the health department will sending the people to the village to do the vector survey. The survey, you can calculate the brutal index, container index, and house index. Those are very old index, actually. Many countries use those index as a warning sign. So if those index higher to certain level, the EPA, the Environmental Protection Agency, will sending people to the village to spreading the insecticide and to also to ask people to reduce the container, the source reduction. So those are the two major ways for the vector surveillance and dengue control. Yeah, and fortunately, although we have the outbreak in 2014 and 2015, but after 2015, we have no case in 2016 because we have intense control measurement there. And after 2019, because the COVID-19 issue, our country is closed. So we have no dengue outbreak since 2016. You know why? Because the dengue transmission in Taiwan is a little different to the dengue transmission in other countries in Southeast Asia. We still call dengue epidemic in Taiwan because the virus always bring by the traveler from other country. Like 2014, the main serotype is a type 2. I think it's Indonesia lineage, I guess. And so you can trace back the virus sequence to know, okay, this year is come from Vietnam, this one virus is come from Thailand. So we need to have the imported cases to trigger the local case. So if no traveler person with our border is closed during COVID-19, so there's no way for transmission. So that's why we don't have the local outbreak since 2016. So that's a very different situation.
Wow, that's amazing because Indonesia still struggle with the outbreak of dengue fever.
Right.
Yeah, it's a vice versa with the Taiwan. Okay, how about the answer, Mrs. Krishna? Is it any further question regarding this? No? Okay, is there any question? Other question? Please, from student or from lecturer, we can use this opportunity to ask Professor Chuang about anything. Hey, I see Mr. Sakundaro Adi is turn on the webcam. Do you want to ask something, Mr. Adi? Oh, I see. Okay, still mute the audio. Ms. Tisa or Ms. Dwi, do you want to ask something? Yeah, perhaps someday we can learn from Taiwan about this. I see. Yeah, in the chat box. Okay, it's still from Miss Na. Minsar, what are your advice for public health workers and the Indonesian government to be able to control dengue fever?
Okay, yeah, I think it's a very interesting question. We also discussed in the yesterday meeting with the people from Bandung. I need to say for dengue control, we don't have too many fancy approach. If we have, we already solve the problem, right? So the control measurements still need to engage the community involvement. Because if you ask people to spray insecticide, it's not the best way because the insect resistance can emerge. So the insecticide is the last weapon we want to use. So we still want to reduce the resource. So the community education is quite important. But we know education is a long way to go. It's not very easy to ask people to do everything you want, okay? And from our meeting yesterday, we mentioned about very important issue for government and public health department is the data sharing mechanism. The interconnected data sharing mechanism should be very smooth. It's because some people from Bandung, they mentioned about the data, the different departments, they don't share data with each other. If your data doesn't share with each other, you don't know the real-time information. You don't know you cannot respond immediately because the delay of data. So it's quite important for government and the health department to sit down together to talk about with each other, to establish a platform how to share data. The interconnection for data, if you overcome this issue, some very outstanding scientists or technician can get involved to use this data to visualize them or to analyze them and to give the first line public health worker the right information. Like for example, if you can identify the hotspot very quick, all the intervention control measurement can go to that place right away. So I think it's a very important part for the government responsibility to make the data sharing pipeline become very smooth.
It's also a big homework for Indonesian government to open with the data. Okay, Mr. Adi, I think you can you can ask now.
Yes, thank you. Hi, Mr. Professor Chuang.
Yeah,
nice to meet you.
Nice to meet you too.
Also, I am interested in what you said in the early of your presentation about One Health in Taiwan.
Yeah.
Could you tell me about your experience, especially in applying One Health and controlling what we call it here, vector-borne zoonosis in Taiwan, especially for the factors that support the success of this what we call control, and also the factors that can hamper the success of the controlling. Can you tell me your experience about this part? Thank you.
Okay, yeah, it's a very important issue, and also we are in a very early stage. The One Health concept has been mentioned about 20 years ago, but actually not many people really focus on this until some outbreaks occur. So the same thing in Taiwan. The Taiwan CDC and the Agriculture Department, they don't negotiate each other because they have a different purpose. The Taiwan CDC, they focus on human, right? The human health is very important, but the Agriculture Department, they care about the money, and the people, the farmer, like the poultry farmer, they need to earn the money from the feeding the duck and chicken. I'm talking about avian influenza. The avian influenza in Taiwan also become a problem because we have outbreak in the poultry every year. So, but we know the avian influenza issue become more and more important. So in 2008 and 2009, the Taiwan CDC and the Department of Agriculture start to work together to think about how to control, how to standardize the feeding criteria for the poultry, how to feed the chicken, how to feed the duck, how to feed the geese. Okay, so that's the first time these two departments start to talk because avian influenza. So I say we are still in a very early stage because I'm also in the project for avian influenza. We also have a problem to access the data because the Department of Agriculture, they are willing to give me the positive poetry, but they don't want to give us the sequence data. So there's still some gap between the Department of Agriculture and our study. So we're still working on that. Yeah.
Okay. Yeah. Yes, thank you very much, Mr. Chuang. Okay.
Thank you, Mr. Adi, for the question. Is there anyone to ask other question? Perhaps Ms. Nisa, you want to ask?
Me?
Oh, okay. Yeah.
Yeah. Thank you.
Please, Martini.
Yeah. Nice to meet you, Prof. Chuang. Yeah, in this meeting, virtual meeting. Yeah. Yeah, but very interesting to see your presentation. And then I have several questions. Yeah, but one of my questions similar with Pak Adi. Yeah, Mr. Adi. Yeah, about One Health. Yeah, I think it's very difficult to combine in the multi-sector like that to gather control the infection disease like that. Yeah, that's my my opinion about the wild animals. Yeah, because they live in the jungle, and then so we hold the head officer like that to handle these wild animals. Yeah, maybe give a limitation interaction wild animals to the human. Yeah. Yeah, that is maybe the similar question to Pak Adi. And then the second, yeah, I want to know about how to measure about the extrinsic period in the vector here, especially in the vector. Maybe yeah, IDS at that time because that's insect is very potential to transmit the disease. Yeah. I often see the period of extrinsic period, but I cannot imagine how to measure because maybe we use the complicated laboratory. Maybe in your lab, maybe it can measure that variables. Yeah. I want to maybe. I want to know about the comparing the insect from Indonesia, Semarang City like that, because I have many experience and also research about this disease, dengue in my city. Yeah, we concern in vector like that. Yeah, so maybe we can collaborate with you to develop the laboratory maybe. Yeah. And then the last how about your opinion with the classical index of entomology? You mentioned about the Brutto index and then host index and the other, because in my research we often found that that index is it's not not correlate with the dengue. So yeah, we can get the experience in Singapore. The index is almost zero, but the dengue case is still high like that. Yeah. Yeah. Thank you. I'm sorry
Yeah.
about any question from me.
Yeah. Thank you. I'm very happy to have further collaboration. Yeah, when you mentioned about the index, that's true. It's also our discussion topic yesterday, because the index we are using right now, house index, container index, food index, those index has been developed 100 years ago during the yellow fever stage. And no newer index has been developed because we don't know whether the new index can help a lot. But I think there's still many things we can work is like for the OV trap. Right now, there are many people use OV trap. And the OV trap density index could be another useful indicator, because in some preliminary study, they show the OV trap index probably not perfect, but better than brutal index and container index. And the other thing we need to think about is we are not just only using the index. We need to think about the surrounding environment of different trap. If the trap put in the urban region, if the trap put in a rural region, or a trap near the building, or a trap near the water body, the surrounding landscape might also have different impact for the mosquito behavior. That's one thought. And the second thought is the nonlinear pattern. So we always use the linear idea to link association between the index and the dengue transmission risk. But what if the correlation is not linear? That would be different. So I think there are still many things those relevant to research. We can try to develop some hypotheses and test them. So I'm very happy to work with you if you have some field work, you have some data, so you probably can have further discussion to how to analyze them. Yeah, so it's very good.
Yeah, thank you. Like with my study, I add the next index, not only the index and then host index. We use a trap index to our study. Yeah. Thank you. For your response, Prof. Chuang.
I saw another question.
Yeah, thank you, Martini. There's other question from from Siti Rahayu, is it? Yeah, from Siti Rahayu. She saw earlier that pesticides are one way to reduce vector population. What kind of pesticide was used? What is the level of resistant value so far? And what is the government policy on this issue in Taiwan? Thank you.
Yeah, in Taiwan, we mainly use the Parasitology insecticide. And in Kaohsiung and Tainan, they were sending the mosquito sample to CDC to test the resistance. So far, we didn't see the very severe insect resistance in Taiwan. But the issue is actually I don't see any publication. I just communicated with people in CDC, and they say, oh, the local government is sending a sample for test, and so far so good. So actually, we have never seen. I've never seen the published paper for Taiwan to study the insect resistance. But I know the local health department, they care about this issue. That's all I know.
Okay, thank you, Professor Chuang, for the answer. Okay, I see the raised hand. Narcis Musafili. You can open your mic, or perhaps the co-host can give the access. Okay, yeah, please.
Thank you, Prof. Chuang, for your good presentation. My question relates to malaria. As we know, malaria is the most important vector-borne disease when you consider its global distribution and the number of people affected, but also the large number of deaths that is causing. So you said in the beginning of your presentation that there is a vaccine. But as we see, the number of death incidents are still high, especially in Africa, but also here in Indonesia, in the east part of Indonesia, we see that malaria is still endemic and is still causing death. So my question is, I'm from Africa. I saw they used several methods for the control of this Plasmodium species, use of insecticide, they used whatever to control. But as you see, the cases are still increasing. Maybe they decreased for one season, but they increase for another season. So another issue is, another problem is regards this vaccine. When I was back there, I didn't see a distribution of or administration of this vaccine to the people. If you have data for this vaccine, you can tell us, because till now, I don't know real data about this one, how about its effectivity and so on. Thank you, Prof.
Yeah, it's a very good question about the malaria vaccine. Actually, currently the malaria vaccine has been applied in Malawi, Ghana, or Kenya, if my memory is correct. It started from 2019. But actually from the clinical trial, phase 3, the vaccine has moderate protection effect, especially for children. They reduce the mortality rate among children under 5. So there are some argument about this vaccine, because for the paper published on New England Journal of Medicine, they follow up the vaccine recipient. They noticed the antibody decreased very quick, probably decreased to 0 in 3 years. But there's also another new evidence to show, okay, although they decrease, they still have memory. So when the vaccine want to go to Africa, the EU, the European Union, they don't agree. But actually, right now, some countries still adopt the vaccination program, but because it's only for 2 years, so we probably didn't see any very significant effect. And just like you say, yes, in Africa, there are some area that have an interannual variation for malaria outbreak. Probably this year is minor, and next year is a very big outbreaks. So it can cause a lot of different reasons. The environment is one reason, the climate is one reason. The other reason is probably due to the unstable political body. In some region, they probably have some war, like Ethiopia. When I went to Ethiopia in 2010, they are quite good, but right now you can see Ethiopia is not very stable. So that's a big issue in many Africa countries, and also affect the disease control. Yeah, but overall, the malaria incidence and prevalence in Africa is decreasing. Yeah, it's overall pattern.
Okay, thank you, Professor Chuang, for the answer. Is there any further question?
Yeah.
I see in the chat box from Dian CN. The question is, in your opinion, what are the endemic risk factors peculiar to Taiwan that can be compared with that of Africa?
Okay, the question is not very clear. What kind of disease you are talking about?
Yeah.
If you are talking about dengue, I think dengue in Africa is still minor issue, because the malaria is the most important one. But in Taiwan, we don't have malaria. So it's quite difficult to compare Taiwan and Africa. And when you mention Africa, Africa, there are a lot of countries. So different countries have different policy and different disease burden. Yeah, so it's very difficult to compare Taiwan to the whole Africa.
Yeah, that's true, Mr. Strong. Okay, is there any question from the participant for Professor Strong? I think we still have time for this. No. From students, epidemiology and entomology. So Professor Chuang, we have 2 major, epidemiology and entomology. Yeah, this is Mrs. Nisa.
Okay, thank you, Mrs. Lintang and Prof. Chuang. In your presentation, you said that about herd immunity in dengue fever. There is has been formed in our society, especially in Taiwan society. Is already formed about herd immunity, Prof. And the second questions, in our study in Central Java, especially we study about filariasis, and we found that Aedes aegypti is active in night or nocturnal behavior. Is there any behavior change to about the mosquito in Taiwan? Maybe in your study is the same result about this, and how they explain about it. Thank you, Prof. Chuang.
Okay. The first question I need to clarify. There's no herd immunity for dengue. I just mentioned about if you infected by dengue, you probably can have short-term immunity for 4 different serotypes for 10 months to 1 year. But after that, you can keep the long-term immunity for the type you get infected. So there's no herd immunity formed in Taiwan. The second question is interesting. You say you capture Aedes aegypti at night, right? Do you think about the effect of a light? We have the light in the house. Yeah, we have a similar experience because the Taiwan is a very high population density area, especially in urban region. And at night, everybody uses the light, so it's like daytime. So that's true. You can capture some Aedes aegypti at night, but it's not a major. I think it's not a major issue. The main activity is still at daytime. Yeah, but sometimes at nighttime we are able to capture Aedes aegypti or Epidemilogy. So I guess probably due to the light.
Oh, okay. Because maybe in our study we found Aedes aegypti is positive with filarial worms. So there is one of interesting things that as we know that the behavior of Aedes is diurnal or just in afternoon or morning. So maybe it can be major factors to the dengue fever, or just dengue in usual behavior, that they can be a major factors in your.
So you talk about you identify the filarial worm in Aedes aegypti.
Yeah.
Oh,
yeah.
That's interesting. So that's the infectious mosquito. Do you have evidence to show they can transmit from Aedes to people?
We just study in our basic study. We just capture in mosquito, but in the people is just we examined about the blood sample, and then and we don't know about the correlation about the Aedes and the in I think in fact between and with the people that we just know about we can found in Aedes the filarial, but in I still confused about if the Aedes can transmit the filarial, they still can transmit the viral. I think the dengue virus in human, or just one parasite that they can transmit, Prof?
In general, the different pathogens, they will compete with each other. So if the one vector infected by one pathogen, so probably have resistance to other pathogen. But it's a general idea, but we still don't know. But I guess probably you identify the filarial worm in Aedes aegypti is probably the accident. So probably the mosquito take blood meal from a patient and they have the worm for the patient. So if you, I think it's only one, right? Or many?
Two, at least two mosquito that positive with filarial Aedes, but the others is, but in we study in Pekalongan city, we found that just Aedes aegypti that positive with filarial worms. Then in other studies shows that collects kinky fasciatus that the potential of major factors in their city, and we have in our study not found the collect kinky fasciatus that positive with filarial. I don't know why, because we examined, in our study we found that Aedes as a potential factors in our study, not collects. Maybe it's accidental.
That's interesting. Yeah.
Maybe it is accidental. Okay, thank you, Prof.
Thank you.
Thank you, Ms. Nisa. Okay, I see the rest hand, but now he is not raised hand. Is there any question? You can use the chat box or raise hand. I see one, and then it disappeared. Okay. Okay, I'm sorry, this is I hold this near the mouse, so it's prior times. It's really a bit noisy. Is there any further question or other new question? Anyone? No? So can I give this closing? Okay. Yeah, I think there's no other question. So thank you very much, Professor Chuang. So to sum up, perhaps I can highlight some of your presentation. Mosquito transmit various diseases worldwide. There are cycles and forest acids origin in zone and in urban. One health is important, collaboration among human health, animal health, and environment. Temperature and or climate effect on life cycle and the extrinsic incubation period. So it's affect not only mosquito, but also in virus. Temperature also, or climate also relate with the creation of habitat and breeding place. There are some of environmental parameters to forecast the vector-borne disease, include macroenvironment for host and environment triangle, such as rainfall, climate risk, and driver mosquito survival and replication of virus. We can use spatial analysis, include spatial components such as visualize our data in space. For example, pinpoint on coordinate location, or visualize vector index, detect the hotspot and do the pre-virus analysis. And also we can apply environmental variables derived from remote sensing data, so it's come from Google Earth, to predict the ecological process of mosquito population dynamic or parasite activities and potential in human race. From the discussion, you can see that in Taiwan on dengue, the epidemic mostly came from travelers from other countries. So the imported cases trigger the local cases. There also need a commitment from our government, Indonesian government, but the openness for data. So the openness to data will make scientists do analysis and be the first line for control measurement. While health in Taiwan, even still in early stage and still some gap from stakeholders, for example, in avian influenza, but they are together working on this issue. About indexing dengue, it was discovered many years ago, but it is still useful. Oh, sorry. There's the one that first time I see it. Wait, I continue here. Maika, yeah, Maika Ayub Hussein, this is international student from master degree. You can ask, you can unmute your audio, Maika. Hello, Maika. Yeah. Still mute. Yeah.
Good morning.
Yeah, it's afternoon, Maika. Good afternoon, Maika. Yeah.
Afternoon,
You can
but
ask.
here, morning.
Oh, okay. Okay then. Yes, please.
It's early morning. That's why we are still in bed.
Wow. Okay.
So my question was, prevention of vector. There is a prevention of diseases. Could be maybe combating the vector, eliminating the vector, or also eliminating contact by human vector contact. Do you think like the malaria, the sleeping under mosquito nets, which prevents contact of human to vector, and maybe eliminating the vector, do you think prevention of contact of human to vector being the best approach in eliminating the vector-borne disease, which is malaria, than eliminating the vector itself? Thank you.
Okay,
Yeah.
thank you, Maika.
It's a good question. To eliminate the contact by the ITN, the bed net, is one of the control measurement to prevent malaria infection. But you know, we set up the ITN, the bed net for people because the biting time for Anopheles is usually at midnight. That's from the previous study. But you know, in some place, in some village in Kenya, they noticed that if you apply ITN for the old population in the community, the Anopheles gambia, they were biting people earlier. So mosquito behavior also can change based on your measurement. So I would say the ITN is still useful, but it's not the only one measurement. And go back to your question is, you know, to eliminate a vector is almost impossible. Yeah, it's impossible to kill all the mosquito. So to block the contact between people and mosquito is easier. So ITN is one approach, and also including IRS, right? And also you have the community education. And with the economic growth, you can put a screen on your house, so you can also block the contact in a rural community. So there are many ways to block the interaction between mosquito and human, and it's much easier than eliminate the mosquito. It's almost impossible. I hope this can answer your question.
Thank you, Professor. It's just that most emphasis has been put on eliminating or preventing contact than also putting more emphasis on vector elimination. It cannot be entirely eliminated, but I'm seeing in my country, I'm from Uganda, East Africa, more emphasis is put onto sleep under mosquito nets, sleep under mosquito nets. More awareness has been put, structured more onto that than telling people clear the breeding grounds for mosquitoes. Thank you so much.
Thank you.
Okay, thank you. Is there any other question, or I continue the summary? No? Okay then. Yeah. About the index in dengue, even though it was discovered many years ago, but it is still useful. The Ovitrap density index maybe is the newest, not perfect, but works. However, it is important to do research on the surrounding, about the landscape of the Ovitrap, like water site, or the kind of species of the mosquitoes, and etc. It is quite hard to compare Taiwan with all Africa, like malaria and dengue. In Taiwan, there's no malaria cases and dengue cases in Taiwan. About dengue found in the night, so it's not like daylight, but it's not the major issue, because the main issue would be whether people do outdoor or indoor activities and at night. And in general, one factor will affect one pathogen only, but it still need further study in human. Changing in behavior is important, but it's not the only effort. So we can still upgrade the education, we do the environment modification. That will be easier than eliminate vector, because it is impossible to eliminate the vector. Okay, is there Mr. Budiara, the Dean is here? No, not yet. Oh, okay then. Bu Martini, shall we wait for the Dean?
Yes,
or...
I'm already.
Oh, okay. Thank you.
I'm sorry.
Thank you.
I'm
So,
sorry.
yeah, please, the Honorable Dean of Faculty of Public Health to give the closing statement for this visiting lecturing program. Thank you.
Okay, thank you very much, Bu Lintang, and the distinguished speaker, Associate Professor Ting-Wu Chuang from Parasitology and Tropical Disease, Taipei Medical University. Thank you very much for your lecturing and already so far. I'm sorry because I have a webinar in the next room. Sorry, so I this time I join not scheduled time. Thank you very much for your information, for your lecture, and I'm very happy you can give some information about the vector control disease to our participant and also our lecturer and our staff. I'm very happy, and this program, our visiting professor program, we designed this event to improve academic atmosphere to the intensive interaction between students of the Faculty of Public Health, Diponegoro, and also lecturer from abroad or from foreigner expertise. And this event, I'm to enrich student, of course, in experience in field of the vector-borne disease. That we know that in Indonesia has so many disease-related vectors. For example, dengue, hemorrhagic fever, malaria, filaria, and also chikungunya, etc. So many disease-related the vector. And your lecture and strategies and also on the program to combat this disease is very important to us. But we realize that many strategies and program in our country also have been implemented, but you know, this disease is still present in our country until now. I think this event is very important, and thank you very much. Important to enrich our knowledge and perspective, and also experiences related to the vector-borne disease and also the control. Thank you very much, Prof. Ting-Wu Chuang. Maybe we can meet in the next event, I hope, and if and I hope so. We can conduct the collaboration between us, between our institution and yours, maybe in field of the education, research, and also in publication. We hope all of you enjoy this webinar, and thank you very much. I'm sorry I'm late.
It's okay. Thank you.
Once again, yes, I hope you enjoy this meeting. Okay, thank you very much. Thank you very much, Prof. J. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, the Dean of Faculty of Public Health. Mr. Chuang, is there any time for one more question?
Yeah, I saw the question.
Yeah, in the chat box. Yeah, it's from Christian from Jambi. So his activity focus on facilitate for indigenous people, especially community live in the deep forest, I think. Based on the past research collaboration with Taiwan, he found 24% of indigenous people who live in the forest have dengue disease. So he asks for your opinion, what is the main factor that they're suffering this disease? Thank you.
Mm-hmm. Yeah, it's quite interesting because it's in forest region, and it's also in the indigenous group. And the 24% is pretty high, but I'm not sure you diagnose the dengue by symptom or by the molecular tool. That's my first question, because the symptom for dengue, Zika, chikungunya are very similar. So actually, okay, by molecular, okay. Actually, I don't know, because it's in the forest region. So you know, the virus also can be transmitted among monkey, and also in the forest region, you probably have different vectors. So those are worth to investigate. Yeah, but it's quite interesting because the area, the city area is very unique.
Yeah.
Thank you.
Thank you, this one. I see. Okay, yeah. This might be the answer. Okay, is there any other question? Ramdan, perhaps? No?
I have
okay.
Professor.
Okay, Maika.
Professor
okay.
talked about
okay, Maika.
Professor talked about, if I heard clearly, about painting houses green to prevent, probably could have been, is it mosquito, something like that? Could there be, if I heard clearly, could there be, could I say, if a pathophysiological, no, the relation, how is that related? The green painting and repulsion of mosquitoes. If I heard clearly, if he said about it, but if I didn't hear clearly, then I can leave it not to be a question. But I heard him say about painting.
Green painting.
Yes.
I probably don't mention green painting.
Okay, then that's not a Thank you. But Professor, I had some researcher here in Uganda, he told me that they came up with a research that looked at paint in the house. That there is some paint they had done research about. That paint, when you paint it in the house, and then the vector falls on, maybe like the mosquito falls on, that mosquito in the shortest time it will die. But he told me when he wanted to, when they wanted to like more publish, to publish the paint, that this paint can kill the vector. There was some interruptions in relation to, there are some people who are more interested in exploitation than preventing the community from acquisition of different diseases through vector prevention. So he told me he was almost blocked from presenting that this paint can actually kill what? The vector. So that's why I asked that question.
I want to clarify, you are talking about the painting.
Yes,
the
paint.
Color of the painting.
Yes.
Actually, you know, like for Aedes aegypti, they like the black color.
The mosquitoes like black.
Especially for Aedes. But it's a well-known knowledge, like the people wearing the dark clothes or the black color. But you're talking about you are painting your house using the different color to repel the mosquito.
He told me the other paint had a fatal kind of chemical probably that kills the mosquitoes.
The similar idea for IRS. They probably put the insecticide in the painting. I don't know.
Okay, Professor.
Yeah.
Thank you so much. Thank you. Thank you.
Yeah, it mostly happened in the bachelor, what do you call it, like a thesis, bachelor thesis in a bachelor degree. They try to correlate the color that mosquito like or dislike. So, but mostly in our student paper, it's mostly about the black color that the favorite ones. I'm sorry. Okay, is there any question from student, epidemiology student or entomology student, please? Because it is then and the prayer of sun and will be noisy. Is there any other? Okay, this is from Nabila, undergrad study. Could the entomology index of dengue, density figure, HIV, ICI, flying in vector control for chikungunya which have a same main factor Aedes aegypti? Does the index range to transmit still same from dengue to chikungunya? Thank you.
Yeah, the short answer is yes, because they are same vector. Yeah. But the issue is just like we discussed about the correlation between those index and this transformation is not it's not consistent. Yeah.
Okay, this is there's a question from our colleague in epidemiology, Mr. Henry. He asked about in the future. For the factor of Borne disease that potential become endemic.
Sorry, can you say again? the chanting behind.
Yeah, it's sound prior. I will write it in text. Perhaps Ms. Lisa can help me.
Okay. Okay. Is there any questions to Prof. Chuang? Hello. Maybe I want to ask one question, Prof, about your GIS geographical. If if the indicators about the density of effect of ID, risk, Pareto container, and house index, can it apply together to the maps? Because in my experience, if I want to compare the three indicators in one maps, it's so difficult to adjust the density level, because as I know that the container Pareto and house index have a difference leveling. So how to make it in one? Can it make in one figure maps in the same area, Prof?
Yeah, we don't have a single answer for this. The first, you want to put these three indicators together. Your purpose is to want to compare them, or you have a different purpose?
To compare. Yes,
okay.
to compare.
You know, for the new GIS software, it can allow you to put these three indicators together. But if your data is too many, for example, you have a lot of villages, a lot of the survey site, the figure will become very messy. So it's not a good idea to put these three together. So I would suggest you probably can compare them to use like a correlation coefficient or something like that, and you process it before you enter the data in your map. You can do some analysis before you show it in the map. Yeah, actually there are many different ways. So at current stage, I have no single answer for this. We can try to see how to put these three indicators together. In my opinion, in my experience in Taiwan, these three indicators usually is very similar. The correlation is pretty high for these three indicators.
Okay, because in our last studies, sometimes we found that in several villages, we found that the house index is high level, and then the container index is low. So sometimes we are difficult to get the conclusions about how the density of IDES factor in their village. So there is the answer is the single indicator we put on the map. There is like this or how? Because it's so difficult when the levelings of indicator is different. We can get the conclusions.
Yeah, actually you can try to combine these three indicators to put different weight. That's I think it's worth to try. If you give different weights to these indicators, you can probably create new indicators. Yeah, because that's what I'm talking about. These three indicators alone is not very good to predict the dengue transmission. But we don't know if we can develop a new indicator. But how to combine these three indicators is also worth to investigate, to dig into. Yeah. Probably you can work with the statistician to ask them, is there any way to combine these three indicators?
Okay, thank you, bro. Okay, this is any questions from Mr. Henry about how the future of vector-borne disease has potential to be a pandemic.
Vector-borne, actually, I have no answer. I was see that the next potential infectious disease might be avian influenza.
Avian influenza.
Yeah,
Again.
avian influenza probably have a higher risk than other mosquito-borne disease. You know, for the disease, you want to cause the pandemic, the transmission ability should be very high. Like a COVID is transmitted by droplet airborne, so it can transmit is very quick. So that's the basic criteria for the pandemic. But for mosquito-borne disease, it's not so easy to have the pandemic.
Yeah, true. Because a lot of factors. Maybe any question, Miss Lintang? Can you? Okay. Thank you, Prof. Chuang.
Okay, sorry for the inconvenience for the prayer sound because my house is near the mosque and it's the prayer time. Okay, I think as a token of our appreciation for Professor Chuang time and his valuable contribution, may I request a big applause for Professor Chuang, please?
Thank you.
Okay, thank you, Mr. Chuang. And ladies and gentlemen, may I thank you very much for your active participation in this program. I hope you enjoy the program. Stay safe, stay healthy. Bye-bye. Thank you, Professor Chuang. And, okay, I'm sorry. You can
Okay. Hello participants, I'm Lara, supposed to be second MC here. Let me apologize sincerely for the technical problem. Okay, thank you Mrs. Lintang for your time, and thank you to Assoc Prof. Ting-Wu Chuang, who has delivered us a great presentation that enhanced our knowledge about vector-borne disease, especially mosquitoes for dengue virus, its environment modification, and the infectious transmission of its disease, mosquitoes vector surveillance and its control. And thank you, Mr. Budiono, for the closing statement.
Yeah, thank you for Professor Chuang and Ms. Lintang for the presentation.
Dear participants, finally we're at the end of this event. Please, operator, be ready. But before closing this event, we would like to invite you to attend. Operator, hello? Yes. This is Seminar Pendidikan Kompetensi Epidemiolog dalam Menghadapi Pandemi that will be held in 17th of September 2021 as seen on screen. And we would like to inform you that all participants will get e-certificate after this event, 1-2 weeks from now. So make sure you have filled in your email in the registration form. Thank you everyone for your attention. Hopefully you will get new insight from here. Last but not least, we as the committee would like to apologize if there were mistakes during this event. Okay, now it's time to take pictures together. I would like to invite all participants here to take pictures together. To all participants, please turn on your camera and the operator will take the pictures. Is the operator ready?
Kamera lagi. Saya foto motornya. Ini kan mulai. Oh.
Hello, operator. Are you ready?
Ready.
Please count into 3.
1, 2, 3. Cheese. Okay. Once
Next
more.
slide.
Okay. 1, 2, 3.
Is there any slide?
Okay, maybe one more slide.
Yes.
Yeah, done. Thank you.
Okay, thank you, operator.
Okay, thank you for the operator, and I hope we can get new insights and knowledge from here. And last but not least, I hope we stay healthy, and see you in the next event.
Have a great rest of your day.
Assalamualaikum warahmatullahi wabarakatuh, and good afternoon.
Good afternoon. Thank you everyone.
Bu Lintang.
Terima kasih.
Ya.
Terima kasih Bu Lintang. Izin pamit. Assalamualaikum.
Waalaikumsalam. Ya izin live.